Hello, everyone. My name is Jean-Baptiste Bale. I'm a research fellow at the University of Glasgow, and I'm going to present you today this talk about time domain instrument simulations, and especially about LISANode and LISA Instrument. So this presentation is also on behalf of the simulation working group, now called the FMT Simulation Expert Group. On today's menu, we'll have three different things. We're going to start with a little bit of context. So what kind of simulation tools we're talking about and how they can be useful to you. Then to get started, we're going to learn how to gain access to the projects and install them and run our first simulation. And lastly, we're going to talk briefly about the simulation models that is underlying those simulators, what kind of results you get from those simulations, and what kind of parameters you can tweak on the simulations. So let's start with a little bit of context. When you talk about simulating things in LISA, there are a lot of things that you can do. You can simulate waveforms or trained time series or in the frequency domain. You can also simulate the instrument itself, LISA. You can simulate the orbits and the dynamics. I don't know, maybe the test mass motion, attitude control, and so on. You can simulate the optics, the response to gravitational waves, the propagation of optical laser beams, noises and signal, maybe artifacts as well. You can simulate the onboard processing, the measurements by the phase meter, the onboard computer processing, and so on. And of course, in the end, the telemetry down to Earth. You can also simulate the on-ground processing, which starts with some kind of data consolidation. This is the famous L0 to L0.5. And then this in-rep, the initial noise reduction pipeline, the L0.5 to L1 part, which encompasses in particular TDI, time delay interferometry. And of course, in the end, you want to analyze your signals. So you want to do some kind of signal detection and parameter estimation. And of course, if you do simulations, you have different objectives. You can, for example, want to test the response of the system during operations before sending a new command, and you do that with an end-to-end instrument simulator. You can also want to generate very quickly templates for your match filtering algorithms during the analysis for parameter estimation. Or you want to generate realistic data. That means going from waveform all the way through the instrument simulation, the on-ground processing, so that you can test or assess the performance of your analysis codes. In this presentation, we're going to focus on generating realistic data, and we're going to focus even more on this instrument simulation part. So let's get started. Just a word about what these simulators are. So LISA Instrument is a Python package based on the usual NumPy and SciPy modules. It's entirely based on the LISANode simulation model. So if you want to refer to it, there's a paper in preparation, or you can refer to Olaf Hartvig thesis. And it includes the simulation of dynamics, so the motion of the test mass and spacecraft. It's currently limited, but it's there. The simulation of optics, so that goes from the propagation of the laser beams, which includes instrumental noises and signals, all the way to the main interferometric measurements and the auxiliary measurements by the phase meter. And then we simulate the onboard processing, so all the way from the digital sampling, the filtering, and the downsampling. LISA Instrument is available for the consortium full members only right now, but there are ongoing efforts to open source it. So currently it requires a GitLab account and full member rights. So usually what you do is you connect to gitlab.in2p3.fr and you sign in with Sibboleth with your institutional email. And then you request to be added to the full members group. And once you've done that, you have access to those projects. It's hosted at the link that you have here on the screen. And you can install directly the package using pip. You just run pip install git plus, and then you input the URL of the project on GitLab. LISANode share the same simulation model as LISA Instrument. As we said, it's implemented in C++ so that we get compiler optimizations and a better memory management. So usually it's a good choice if you want to run long simulations with a lot of different effects enabled. If you want to run short and quick simulations, I'd advise that you use LISA Instrument, as it's easier to install and easier to use. It's hosted at this address, and you can clone the project with git clone with the address here and install the package with pip install LISANode. So let's see how you run a first simulation with LISA Instrument. As usual, you start by importing LISA Instrument package. Then you instantiate an instrument object to set the simulation parameter. So here we set the simulation size, the sampling rate to 0.5 Hertz, and then we use some Keplerian orbits. You run the simulation by just calling simulate on this object. And optionally, you can write the results to an HDF5 file, which here is called mysimulation.h5. And that's it. If you want to have a quick look at the results of the simulation, all of the time series are saved on this object instru. So for example, you can plot the beat note frequency fluctuations using plot fluctuations, or you can plot the inner spacecraft carrier beat notes from one of the MOSAs, let's say 1, 2. So you just use instru.isc carriers 1, 2. Or you can use PyTDI to compute the usual Michelson X, Y, and Z combinations. So you just import PyTDI and the data interface. You can load directly the data from the mysimulation.h5 file that you just created, and then you compute X, Y, and Z. Refer to the documentation of PyTDI for more detail about this. And now just a few minutes to quickly brush over the simulation models that underlying all of those simulations. We're going to start with a little bit of convention. So the spacecraft are labeled 1, 2, and 3. But as you know, there are 2 MOSAs per spacecraft. So we have to use this double index convention, where the first index is always the index of the spacecraft it sits on. And the second one is the index of the spacecraft it looks at. And then all the signals just carry these double indices of the MOSA they're attached to. So it's pretty easy. The simulation in LISANode, in LISA Instrument, sorry, is staged. So that means that we start by simulating the noises, then we generate the local laser beams, we propagate them to the other spacecrafts. Then we propagate them inside the optical benches, all the way to the interferometers so that we form the beat notes. And then we simulate any onboard processing, like filtering and so on. Of course, various effects can be toggled, activated or disabled. There are instrumental effects like the locking of the different lasers, the clock drifts and jitters, the Doppler effect, the filtering we just talked about. And you can also enable or disable different noises, laser noise, for example, or the dominant noises, the test mess or the shot noise, and also other secondary noises like optical bench path length variations or the backlink between the 2 adjacent MOSAs. An important thing to know is that in the simulations, we use 2 different sampling rates. By default, all the physics, the optics and so on, are simulated at 16 Hertz. And the measurements in the end are downsampled to 4 Hertz. So the products that you get from the simulation are sampled at 4 Hertz by default. Talking about the simulation products, it is important to know that everything is expressed in terms of frequencies, and the frequencies are actually computed as 2 different quantities, separate quantities. The large offsets, the large off-band frequency offsets, usually which you don't really care about, and the small in-band frequency fluctuations. This is where you find most of the noises and your gravitational wave signals. Of course, the total beat note frequencies can be recovered at the sum of those offsets and fluctuations, and they're available in the simulation under the name total. You probably know that the laser beams are modulated in LISA so that we have to propagate a carrier, which is the main signal, the one that most of you are interested in, which itself is expressed as a frequency offsets and fluctuations, and an upper sideband, which also contains a frequency offsets and fluctuations. So in the end, We have a bunch of interferometric measurements expressed as bit notes. So we have 6 carrier bit notes for the 3 interferometers: the inner spacecraft, which contains the gravitational wave signal, the reference, and the test mass, expressed as offsets and fluctuations, and the 6 upper sideband bit notes for the same 3 interferometers, again, as offsets and fluctuations. I hope that explains a little bit what we just saw when we run the first simulation. Of course, this is a very quick intro on the simulation. So if you want to learn more, there are a few references. The main one now is the LISANode simulation model document, which is available on the LISANode repo, also available at this address on Overleaf. There is an entire section in Olaf Hartvig's thesis, and there's a reference paper in prep by Olaf and myself. And I wanted to talk about, as a last point, about the simulation workshop that took place in March 2022, where we talked in detail about all of these models and the different simulation tools. So if you're interested in it, please reach out to the simulation expert group chairs to access the content. And if you missed it, don't worry. If you want to attend, it's going to happen next year again. Thank you very much.